We have several flash talks for poster presentations. So can I have, I don't know the first names, but Boss come forward?
He told me earlier that he will not be presenting the lightning, but he has a poster outside, so make sure to check that. So you can go to the next one.
The next one, Weiss.
Good afternoon. My name is Trevor Weiss. I have been working with Dr. Joel Zinn at Cal State University Long Beach and working with the Roman Astroseismology Wide Field Science team on creating a population yield of astroseismic data at the galactic bulge for the Galactic Bulge Time Domain Survey. So the purpose of using astroseismology, there's a lot of science that could be used to get a lot of data. Some of them could be microlensing exoplanets. You could also determine stellar ages. I don't have a lot of time, so I'm going to let Mark Pinsino do that tomorrow. So he'll be going into a lot of those details for that, so I hope you can attend that. What I am going to talk about, though, is the simulations that we ran in order to get these astroseismic data detections. So we used a model created by Sanjeev Sharma called Galaxia that goes ahead and does a survey of the Milky Way galaxy, simulated survey of the Milky Way galaxy of stellar objects. We went ahead and applied a noise model by Gold and amplitude predictions by Hubbard to go ahead and make a signal to noise ratio prediction, as well as set these cutoffs of stellar objects that have temperatures less than 5,250 Kelvin, nu max is greater than 5, and signal to noise ratio is greater than 15. If I have this here, cool. We also went ahead and used fields of view based on Matthew Penny's work. He had set up 7 fields of view. We added additional 2 in order to comply with the 15-minute cadence and the nominal slew times. And it added an additional 10th field of view that's not included in the data, but we wanted to show off anyways at the Galactic Center. I know there's some talks of a possible extra field of view at the Galactic Center, so we wanted to see what kind of astroseismic data we're going to get there as well. You can see our fields of view down below here. It's a little bit small, but you can see the poster out front has a little more detail with that. We've added 2 to the left here of Matthew's 7 that he set up around here. The figure to the right here, you can see this better outside as well, is going to be our population yields per field of view. Green indicates Matthew's field of view. Blue indicates our additional 2 fields of view, both again running at rolling angles of 0.281 to accommodate with Roman. And we have this red one down here, which is our Galactic Center. Also to the right, though, is an estimate of stellar mass, Earth mass exoplanets. The counts of those within each field of view, so that's going to be shown in the gray bars here, and that's going to be on the right-hand side here. So how many stellar objects did we get for astroseismic data? We simulated about 2 million objects, stellar objects within the Milky Way, and within this field of view. Of the 2 million, we got detections of about 437,000 astroseismic data. You also have about 294 objects that are at the bulge, or considered part of the bulge. You can see that up top here, that here's our HR diagram showing the full population, and here to the right is our detections. And so you can see that our detections are kind of found in this area here, which is considered the red clump. We can assume this is the red clump right by here. Feel free to look at all our data. It's really exciting stuff to get our populations. We see that AMR values do have an effect of age metallicity relations. And additionally, Noah Downey is going to provide some light curves in his poster presentation as well that will help us with our noise models to fine tune our results in getting those population results. Thank you.
Thanks, Tom. Okay, next up we have Dalal.
You. Hi, everyone. I'm Nihar, and I'm going to be talking about work on baryonic feedback that I've been doing with Chen Hao and Chris at OSU. So in the context of cosmological simulations, baryons are really hard to model, but they are really important in the era of precision cosmology because they suppress the matter-power spectrum at small scales, or which you can see on this left plot. But our hydrodynamical simulations are really bad at predicting this extent and strength of this suppression. And because of different implementations of baryonic physics, they all have different predictions. And what this leads to in our cosmic shear analyses is scale cuts. Basically, anywhere where we're uncertain about what these suppression effects are, we take out of the actual data that we're able to measure. So this you can see on the right, which is from Dark Energy Survey Year 3 data. And this is going to be even more true for Roman, which will be even more precise and probe structure to even smaller scales. So what we're proposing is a new model. It's a pretty uncreative name, the dark matter plus baryon model. But the motivation behind this model is that it's flexible enough to describe all the suppression levels that you see in different hydrodynamical simulations that people use today, but also has some physical motivations. It's a pretty complicated model. It has a lot of parameters, but we're hoping to actually constrain this using data from like a lot of different probes of different kinds of physics, I guess. And so the one I'm particularly working on is the thermal Sineev-Zeldovich signal, which is a secondary anisotropy in the cosmic microwave background. It's basically a measure of the electron pressure in the hot gas and galaxy clusters. And so the idea is to basically extract the cluster profiles from noisy CMB data and then characterize how the signal depends on mass. And using that characterization of this mass observable relation, you can basically fit parameters and then predict suppression of the matter power spectrum. We have some forecasts for Roman and as well as current like dark energy survey data. So for the dark energy survey, we do a really good job of constraining cosmic shear to like around this 0.1 sigma level, which is exciting. So for current surveys, this is great. But right now, based on our Fisher forecasts, we aren't quite within the 1 sigma level for Roman. And so we definitely want to do more work, maybe better constraining this model. And I'm definitely interested in talking to people about like other possible probes that can help constrain this model. So please do feel free to come find me at any of the breaks. Come see my poster downstairs if you want more details. Thank you so much.
Thanks very much. So next we have Wynn.
Thank you. Hi, my name is Catherine Wynn. I'm from the University of Washington, and I've been working with Professor Ben Williams on a kind of Roman observational planning tool as part of the Roman Infrared Nearby Galaxies survey team. So we've been developing this pipeline which essentially will take an input catalog and run it through the STSCI STIP simulation software. And so all of the mock Roman observations will happen kind of in parallel. And then the goal of this software is to then put these output observations through photometry software to then, so we can see, compare to the user input catalog that we've input, do we actually see what we expect to see? So we've been specifically doing this with dwarf galaxies. We've been making them using a tool called Walter, and where you can kind of set the ages and the metallicities and the masses that you want to do. So on the left there is a age and metallicity spread of one of the galaxies that we made, and then there is a color magnitude diagram of one of the galaxies with the color map for the metallicities. And that blue line there is about where we would be able to, the lower observational limit for a 1 hour exposure, because all of these dwarf galaxies that we've been using have been set at 4 megaparsecs away. And so I'm running through this kind of quickly because I only have 3 minutes, but essentially this is our results so far. We've been focusing on a mass range of 10 to the 4 to 10 to the 6 solar masses, which you can see in that grid in the middle there. And then on the top two images kind of show those extrema. So 10 to the 4, you can just about see a smattering of stars, and then 10 to the 6, it actually looks kind of like a galaxy, maybe. But then on that, STIPS also has capability to add all the background galaxies and noise and everything that you would kind of see in a normal observation. And so we've put a 10 to the 5 solar mass dwarf galaxy in there as kind of an example of these might actually be quite hard to see. And so the goal is to, again, like put these output images through a photometry software like Dolphote to then be able to properly plan our observations, because we'll know down to what mass limit we'll be able to see. Thank you.
All right, thanks. Yeah, last but not least, Van Dyck.
Hi, I'm Skylar Van Dyke here at IPAC Caltech, and I believe I'm keeping you all from lunch. So I'll try to move through these slides rapidly. So I have a poster downstairs on RAPID. RAPID is the Roman alerts promptly from image differencing. We're one of the Roman project infrastructure teams. We're a highly co-located team between IPAC and the Cahill Center for Astronomy and Astrophysics. So there's basically 2 or 3 buildings between us, all on the other side of the street. And Mansi Kazalwal is our PI. So our main intent is to enable time domain science from Roman. And our goal is to provide 4 services to the Roman community. Rapid image differencing of every new Roman image, Roman WFI image from a reference image. Prompt public alert stream of all Roman transients and variable candidates. Source mash light curve files for every identified Roman candidate. And force photometry services for photometric history at any observed location. Low latency is the highest priority for RAPID. Our intent is to get the calibrated level 2 data, Wi-Fi data from the Science Operations Center within 48 hours. The process of doing so is still TBD. And then execute image differencing and alert broadcasting within an hour after that point, which would also include initial source classification via machine learning. We are going to offer force photometry on difference images and light curve history within about 24 hours, and all of our data will be inevitably archived on MAST. This is just a block diagram of our conceived pipeline. We want to interact with you in the community here. RAPID wants input from you, so please sign up for our announcements from RAPID. Send us email if you have any question, visit our website, and join our RAPID Slack. We really want your input and feedback. And as a shameless plug, RAPID is still growing. We're hiring. We're currently looking for an application developer, early career, and we will be hiring a staff scientist as well. And we look forward to any potential candidates that you might know. Please push them our way with further opportunities in the next fiscal year. Thank you.
All right, so that concludes our morning session.
Right.